Alright guys, this is part 2 of chapter 19 and 21. We're just going to finish up the examples today. So, number 2 says Johnny Seeds claims that their gold star yellow squash has a germination rate of 97%, and a random sample of 400 seeds, 99% germinated. At an alpha equals 5% level, is there enough evidence to support the claim that the germination rate is higher than 97%? So, step 1, our null hypothesis. We're talking about percents here. So really what we're going to have is we're going to have a P. Okay, so our P here is equal to 0.97. Or you could write 97%. That's fine as well. Okay. Our alternative here would be that it's greater than 97. It wouldn't be that it is 99. It'd be that it's greater than 97. So our alternative hypothesis, P is greater than 0.97. Alright, now we need to check the conditions here. Some of the conditions we need to check. We need to check to see is NP and NQ greater than or equal to 10. We've got to check and see that we're sampling less than 10%, or less than 10% of the population. So Johnny Seeds is a really big seed company. They're who I get all my seeds from. Those weren't obviously Gold Star Yellow Squash seeds. I believe that was actually Butter Crunch lettuce seeds, but they make a whole bunch of seeds. 400 seeds is a drop in the bucket for them. So we got to believe that we're sampling less than 10%. If we want to check NP and NQ, you could do 0.97 times 400 and 0.03 times 400 if you want to do that real quick. I'll come over here to the calculator. We can do 0.97 times 400. That gives us 388. And then we'll do the Q, which would be here. It would be 0.03 times 400. And that would give us 12. 12 is greater than or equal to 10, so we're okay. Our initial conditions hold. We also need to check that it's randomly chosen. We need to check that that each of the seeds are independent of each other. But if you check all those, you should find that your initial conditions here are okay. So we want to test our data. Which do we use here? Well, it's a percent, so we really only have one choice. The conditions are met, so we're going to use the one prop z-test. Okay. So next thing we need to find here is our p-value. So that means we need to run the whole system through here. So if I pull up my TI, I hit stat, go over here to test, scroll down to 1 proportion z-test, which is number 5. My p-value here, okay, p-naught. P-naught is going to be, P-naught is going to be your initial P here. So if you want to even write this as P-naught, that's perfectly fine. So P-naught here is equal to 0.97. 0.97. Okay. X here. If we pull this back up, let's try to find our X. Okay. Now, what we have here, we have 400 seeds germinated, or out of the 400 seeds, 99% germinated. We don't have an X value here. Remember, X is just your N times your sample P. So it'll be 400 times 99. So 400 times 0.99. And it has to be a whole number. Here, it is a whole number. So the whole number is 396. Now your N here was just 400. And the direction of our test here, if we go over here, we see that we want P to be greater than 0.97. So I'm going to select greater than, which is the last one. Okay. Other than that, all you have to do is hit calculate. And the p-value you get is not the p-hat. The p-hat is your sample proportion value. The p-hat there, or the p that we're looking for here, is the p equals 0.009517. 5649. Okay, so I'm going to write that over here on this. So the p-value we got was 0.009. What else was it? It's 0.00951, We'll round it to 2, 952. The reason that I didn't round this to 0.01, or 0.01, is here the alpha is 5%, so it really wouldn't have mattered. But if your alpha would have been 1%, then technically your p-value would have been less than 1%. But if you'd have rounded it, you would have thought it was the same thing. So you could have ran into some issues there. So a lot of times I try not to round my p-value anywhere close to what my alpha value is if I can help it, because the little differences make a big difference in the end. Okay, next thing we have to make is our conclusion. So our alpha value here that we're using is 0.05. That's just straight from the problem. Or you could write 5% if you'd rather. P-value, once again, if you want to rewrite it, is 0.00952. Alright, so we got to decide whether we're going to reject the null hypothesis or fail to reject the null hypothesis. Alright, so here we've got P, which is 0.00952. What is its relationship to alpha? Okay, so here P is less than alpha. Okay, so since P is less than alpha, we are going to reject the null hypothesis. So the decision we would make would be to reject the null hypothesis. Alright, so we've made our decision. Our alpha is bigger than our p-value, so we've rejected our null hypothesis. All we have to do now is write it in a formal sentence. Now, I'm not going to attempt to do that with this little cursor hand thing because I don't have the right pad. I just have to do it with the click of the mouse when I'm writing. That's why it looks so terrible. So I'm going to put it up on the board real quick, and I might write a few other things out as well when I do that. But there it is for you. So if we're going to put it in a complete sentence with an alpha equals 0.05 significance and p equals 0.00952, I reject the null hypothesis. The data suggests that there is significant evidence to support the claim that the germination rate of Johnny's Gold Star Yellow Squash is greater than 97%. You want to say is greater than 97%. You don't want to say that it is 99%, for instance. All we've shown is it's greater than 97%. That doesn't automatically mean that 99% is our new percent. We just know from our test that it's greater than that initially thought 97%. So that's how I put that. There's several other ways you can word it, but this is a good way to word it here. Alright, number 3 says in a healthy pond, an average bass weighs on average 3 pounds. You decide to take a random sample of 23 bass and find the mean to be 2.7 pounds with a standard deviation of 0.3 pounds. Determine if the pond weight is less than average and indicates an unhealthy pond. So we're going to let alpha equal 0.05 here. So our initial hypothesis, our null hypothesis here, would be that it's a healthy pond, right? So what we're going to do here, our null hypothesis, is that mu, and I'm going to write mu naught, is equal to 3 pounds. Okay, our alternative hypothesis here says determine if the pond weight is less than average. So we're going to say alternative hypothesis is that it is less than 3 pounds. Okay, I want to check our conditions here. The fish need to be independent of each other, which actually might be hard because one fish might cause another. If one fish eats more than another fish, it could be taking, nutrients and food away from other fish. We also need to make sure that it's chosen randomly. So, make sure you check your initial conditions. If something just seems way off, make a note of it. But here we're going to say, okay, we hope these fish are independent of each other. Hopefully the researcher that decided to choose these fish chose them randomly, and we're going to hope our initial conditions hold. Let's test our data. Which do I use? Do I use one proportion z-test? No, because this isn't a proportion. It has a mean. So therefore, we're going to either use z-test or t-test. Okay. So if I'm looking at it, I've only sampled 23 bass. So that starts to point towards t-test. Okay. In the random sample of 23 bass, we found the mean to be 2.7 and a standard deviation of 0.3. It doesn't say what the population standard deviation is, so that tells us that we're going to have to use that sample standard deviation and therefore use a t-test. Okay, so next thing we have to do is determine the p-value. So if we pull up our calculator, we just have to type everything in. Okay, we're going to hit stat, test, t-test. Okay, we're going to do it by the stats. So our mu naught here was at 3 pounds. Our sample that we found was 2.7 pounds. And our sample standard deviation was 0.3 pounds. We sampled, I believe, 23 bass. And I'm going to go back and check all this really quick. Yep, 3, 27, or 2.7 and 23 here. So we're all good so far, and we've got an alpha 0.05. So we are going to choose, let's look at this other thing. It's the less than sign here, so that's the sign we're going to choose here. So we need to go and select it. It's number 2. And then we're going to calculate. So what we get is we get a P equal to 4.323772393, but it's e to the negative 5, and that's very important. You really have to take into consideration this e to the negative 5, or you will most likely get it wrong. So the p-value here is actually 0.00004. Okay, so let's write that, because we have to move this decimal place 5 to the left. So I'm going to come back over here. So our p-value is actually 0.00004 and a 3. We'll round it there. Alright, so like I said, you have to be really, really careful with that p-value. If you'd wrote 0.43, you would have obviously got it wrong, and you would have got your conclusion wrong. So, or if you'd have just written 4.3, you'd have really, really got it wrong. So we got to make a conclusion here. We're using an alpha significance level of 0.05. Our p-value here is 0.00043. Okay, so if I look at it, I need to compare the two. I've got a p, I've got an alpha. Okay, my alpha is clearly bigger than my p here. So when the p is less than alpha, I am going to reject the null hypothesis. Okay. So the only thing we have left to do here is put it in a formal sentence. And like I said, I'm going to go do it to the board for that. I have a hard enough time writing with this mouse clicker. I'm hopefully going to get me a handwritten notepad thing where I can actually write on the computer. But that's way far in the future. Y'all won't get to see this semester. Maybe the kids next semester will. So let's go to the board and put it on the board. So this one's written a little differently, but the main thing is you get these several important elements in there. So you can kind of see a common range of elements through all these that I'm going to do today. So it says there's significant evidence to suggest that we reject the null hypothesis mu naught equals 3 with an alpha equal 0.05 significance and a p-value equal to 0.000043. The data suggests the average weight of fish in the pond is less than 3 pounds, indicating an unhealthy pond. So biggest thing, you really want to state whether you reject or fail to reject your null hypothesis. Okay, you need to state your significance level, you need to state your p-value, and you need to have a sentence kind of relating it back to what the actual question was asking. So, there's an example right there of it. Question number 4. A real estate agent trying to sell you some land tries to convince you that the land has a value of $5,000 per acre. You don't believe her assessment of the property value, so you take a random sample of 20 nearby properties that have been sold in the last year. Below is the cost per acre of those properties. So basically what we have on this one is we've got an entire list here of different property values. Okay, so instead of inputting statistics, we're actually going to have to input the data. Okay, what we also notice here is before we can do any of this, we've got to figure out, 1, our null and alternative hypothesis, but 2, we've got to figure out what test we're going to use, right? Well, we're only doing 20 properties. I don't see a population standard deviation. This is a number, it's not a percent, therefore I'm going to use t-test. Let me get my marker ready. Let's see if that worked. Yep. so I'm going to use t-test. Let's write our null and alternative hypothesis. So the null hypothesis is that the real estate agent is right, and that it truly is, our initial null hypothesis is that it is equal to $5,000 per acre. Okay. This next part, the alternative hypothesis for this one, and I'll write a null here, just a little 0 to go right there. The alternative hypothesis really requires you to think a little bit, okay? So here it says you don't believe her assessment of the property value. It doesn't say you think the property value is higher. It doesn't say you think the property value is lower. Now, if you're like me and you're kind of a cheap person and you always want to pay the least amount for everything, because that's exactly what I like to do, and you like to hassle things down, you're always going to say that $5,000 is too high. But that's not exactly what the problem says here. The problem says here that you don't believe her assessment. You could believe that $5,000 is a really good price and that her assessment's actually too low, and you're going to buy it because her assessment's too low. And you want to make sure that your reasoning's right. But it doesn't even say that. It just says you don't believe her assessment. It doesn't indicate whether you believe it's too high or too low. So what we're going to write is our null hypothesis here is, or our alternative hypothesis here is that mu is not equal to 5,000. Because we don't know if we want it to be higher or lower or not. Obviously, if you're buying, you might want it to be a lower cost per acre. If you're selling, you might want it to be a higher cost per acre. But it doesn't necessarily say that. You might want to buy low and sell high. So, I mean, if it doesn't outright say less than or greater than or lower than or bigger than, then just go with the not equal to. Okay. Still need to check the conditions here. You know, is it independently? Did you independently choose your properties so that one property value doesn't affect the next? Are they independent of each other? The properties, when you chose them, were they randomly selected, or did you really just pick the ones that you wanted to pick? So you need to check your conditions. You really can't help much on this end once they've already done the selection. So we're going to assume they're okay. Like I said, we said this one was a t-test. We already went through the logic on that. Next thing we have to find is our p-value. So what you're going to have to do, and I've already done this part, so I'll give you a little pause when we get there. But what you're going to have to do is you're going to have to hit stat, edit, and you're going to have to type that list in that they gave us right here. So this list from $2,300 all the way to $2,560. You're going to have to type that in here. I've already done it. I didn't want you to sit here and watch me try to fiddle through and type in those 20 items. I feel like that was kind of pointless. But I will take a pause right here for you to type those in if you need me to. Just hit the pause on your YouTube video. Alright, we're going to assume that you hit a pause there and you got all those values in. We said it was t-test. So we're going to go over here to test. Go to t-test. And instead of pulling in stats, we're going to pull in the data. The only thing you have to type in once you pull in that data is what is your initial, what is your mu naught here? We said that was 5,000. Okay, we've got that. Make sure you pull in the correct list. Here we typed everything into L1, so that's fine. The frequency does need to be set at 1. Now, we said it was not equal to here. This part here says not equal to, so that's what we're going to choose on the calculator as well. We're going to go down here and we're going to hit calculate. And it's going to tell us that mu not equal to 5,000. That is our that is our alternative hypothesis here. Our p-value here is 0.8503005497. I'm going to round it to 0.85. Okay, so if I come over here, p-value of 0.85. That is an 8, drawn as best I could draw it. Now, we have to make a conclusion here. Okay, the alpha level we decided to use here, it doesn't even give us an alpha level. It will give you an alpha level in any of the problems that you choose to do, but I'll show you what to do if you do wind up in this case in the real life. So it says, make your conclusion. Do we reject or fail to reject the null hypothesis? Okay, the p-value we have here is 0.85. Okay, typically our most common used alphas are 0.05 and 0.01. But if I'm looking at this here, right, p-value is going to be between 0 and 1. If I'm looking at it here, if I use any reasonable p-value, right, you're not going to use a p-value that is any, you're not going to use an alpha value that is any bigger than this p-value, because it wouldn't make any sense. So honestly, with any reasonable alpha value here, your alpha is going to be less than your p for any reasonable alpha. Like I said, all your examples that you'll have to do for testing, quizzes, and homework should have an alpha value on them. But in real life, we're not always given an alpha value. But sometimes we wound up in a case like this, where if you choose any reasonable alpha, if this would have been 0.05, 0.05 is definitely less than 0.85. If it would have been 0.01, 0.01 is definitely less than 0.85. If it would have been 0.1, so if you'd had an alpha level of 10%, it still would have been less than 0.85. If you'd have been alright with being wrong 15% of the time and your alpha value would have been 0.15, then it still would have been less than p. You see what I'm saying about any reasonable alpha? Okay, you're not going to want to be wrong more than 85% of the time. So you're going to be okay with any reasonable alpha here. So what we're going to do, alpha is less than p for any reasonable alpha. Therefore, we are going to fail to reject the null hypothesis. Okay, so now we need to put that in a sentence. So let's go to the board and put it in a sentence. So with a p-value of 0.85 and any reasonable alpha value, we would fail to reject our null hypothesis. The data does not suggest that property value is any different than $5,000 per acre. That would be a good way to put this particular question. Next one says Chick-fil-A claims there's 440 calories in a one sandwich serving of a Chick-fil-A sandwich. A local group protesting Chick-fil-A claims that the chicken is too delicious to only be 440 calories. A sample of 15 sandwiches is sent to the lab to be analyzed. A mean of 442 calories and a standard deviation of 3.16 calories was computed. Using an alpha equals 0.01 level, let's test the claim. So what is our null hypothesis here? Our null hypothesis, where's my cursor, is that it is 440 calories. So our mu naught would be 440. Okay. That was a very ugly zero. Alright, so it says that a mean of 442 was found, but it also says the chicken is too delicious to only be 440. So it thinks that our mu is greater than 440. So hopefully you're able to gather that from the question. So we think it's greater than 440, or the protest group thinks it's greater than 440 calories. Okay, we check our conditions here. Remember, we need to check, make sure the sandwiches were independent of each other, that they were randomly chosen. So just be sure to check your initial conditions. Hopefully they all follow through. If something's way out of whack, make sure you make note of it. Otherwise, you cannot help how the surveyor does it. Now, if you're out on your own doing your own survey and you're doing your own sampling, make sure you do it correctly. These are definitely conditions that are worthwhile to make sure you do right so that you can draw correct conclusions. Let's test our data. Which one are we going to use? Well, we only had a sample of 15 sandwiches. Okay, a population standard deviation is not known here. Okay, we do have a sample one that calculated. So we're going to wind up using a t-test. Alright, p-value here. Okay, so that means we got to type everything in our calculator to find our p-value. Alright, so we're using a t-test. So I'm going to go stat, go to the right to test. We're going to use t-test. Okay, so we're not using data anymore. We're actually typing in the stats. So you're going to want to go back to stats and highlight that. I'm going to clear out my mu naught here. My mu naught initial was 440. My sample found that it was 442. My sample standard deviation here, I believe, was 3.16, 316. in here, we decided to sample how many of these? 15 sandwiches. So my in here is 15. And we think that it's greater than, because we want that to match exactly what we had over here on our problem. Okay? Now we're going to calculate. Okay, and what we get is a p-value that is equal to 0.1 or 0.0139880896. Okay, so our p-value, we don't want to round it to 0.01 because our alpha value here for this problem is 0.01. So we'll go out a little bit further. We're going to round it to 0.014. Let's do that. 0.014. 0.014. Okay, so we need to make our conclusion now that we have our p-value. Our alpha value here is 0.01. Our p-value here is 0.014. This one is extremely close. That's why I decided to go out at least 3 decimal places for my p-value here, because if I didn't, they would wind up being equal. And a lot of times when people say they're equal, they're not truly equal. It's very rare you wind up with them very truly equal. So we can see here that your p-value is actually greater than your alpha value. Okay, so if your p-value is greater than your alpha value, what are we going to do? We are going to fail to reject the null hypothesis. Okay, p is greater than alpha, we fail to reject the null hypothesis. That's simple. Okay, what you will notice here, if your alpha would have been 0.05, you would have made the other decision. You would have rejected your null hypothesis. So the alpha value can make a really big difference if your p-value is kind of small. Okay, so here we use the alpha of 0.01. We're winding up failing to reject our null hypothesis. Like I said, if our alpha value would have been different, if it had been 0.05, we would have rejected our null hypothesis. So you got to know what your alpha value is. In some of these problems, in problems like the last one, it didn't so much matter. In this one, it matters a lot. It could change our whole decision. So what we need to do here, we need to write it in a formal sentence, which I'll put on the board. So with an alpha equals 0.01 significance level and a p-value of 0.014, I fail to reject the null hypothesis. The data does not suggest the amount of calories in a Chick-fil-A sandwich is any different than 440 calories. That's simple. So, like I said, y'all are doing most of this stuff online for the rest of the semester, so you're not going to really have to handwrite out a sentence, but you should at least know what one looks like. Biggest thing is state your alpha, your p-value, and your decision, and really make sure you relate it back to the question, because when it comes down to it, you're trying to answer a question. If you don't answer the actual question, if you just give your boss, for instance, I failed to reject the null hypothesis, they're going to say, what the heck is the null hypothesis? What are you talking about? What was your decision? I sent you out there to do all this research. Give me the darn decision. Okay, I've had that happen in several of the jobs I've worked, and tried to break the math down for them. What it really comes down to, most of them don't care about the math as long as you get it right. They really more or less care about this last sentence for the actual decision that you make. Right. In the 1900s, it was generally believed that congenital abnormalities affected about 5.2% of the nation's children. Some believe that the increase in the number of chemicals in the environment has led to an increase in the incidence of abnormalities. A recent study examined 384 children and found that 28 of them showed signs of abnormality. At the 5% significance level, is this strong evidence to support the risk has increased? So, step 1. We're looking at percents here, right? So we need to find our null and alternative hypotheses here. I'm going to move this because it seems to be shaking a little bit. So our null hypothesis here, like I said, we're working with percents, so we're going to use a p. You can use a p naught if you'd like, or you can use just a regular p, as long as you know what you're talking about. So here, p is equal to, you can write 5.2%, or you can write, well, I'll write 5.2% just to be a little different than what I did last time, but you can write 5.2%, or you can write 0.052. Either's fine. Just try to stay consistent. I'll write it in percent for the people that like to write it in percents. Okay, your alternative hypothesis here. What they were looking for here is an increase in the incident of abnormalities. So they think that it has increased. So they think it's going to be greater than 5.2%. Alright, so here's the important one where you actually have to check conditions. You have to check that NP and NQ are greater than or equal to 10. And NQ okay, I'm not really good with Q's. So they need to be greater than or equal to 10. Greater than or equal to 10. Okay, so if we do that, we're going to come over here. We've got 384 children. 28 signs of them showed signs of abnormality. If we're using 384, we really need to multiply that by that 5.02. So if we come over here, 384 times 0.052, we wind up with the NP and the NQ being perfectly fine. Because if the smaller one works, the bigger one's going to work. Alright, so our initial conditions are going to wind up being fine here. Okay. We need to test our data. Which are we going to use? Obviously, we have a percent or proportion, so we're going to use one prop z-test. Okay, easy decision there. So if I pull this up on my calculator, I'm going to go stat test one prop z-test, which is number 5. Okay, it asks for p-naught. P-naught here was that 5.2%. You know you have to write it as a decimal, so it's 0.052. Okay, our X here. Now our X comes straight from the sample that we wound up taking. Okay, so we studied 384 children, found that 28 of them showed signs of abnormality. Therefore, 28 would be your X. So X is 28. And our N here we said was 384. Okay. Now this needs to match exactly what we had in the problem over here, which is greater than. So greater than is already selected, but if it wasn't, you would just come over here and put enter, scroll down and calculate. And what you find is you have a p-value. Now p hat is not what we're looking for here. We're looking for the p-value, which is just the p. So p equals 0.0324. Okay, so that's what I'm going to round it to. 0.0324. 0.0324. 0.0324. Okay, so we got to make a conclusion. The alpha level that we're using here is 5%. So alpha is 0.05. Okay, p-value here we said was 0.0324. Alright, and that means that if I compare the two, alpha is greater than my p. Okay, if alpha is greater than my p, I'm going to reject the null hypothesis. Okay, that's simple. Got to know your rules. Now all we have to do is put it in a complete sentence. So let's go to the board and do that. Alright, so with an alpha equal 0.05 significance level and a p-value of 0.0324, we reject the null hypothesis. The data suggests there is significant evidence to support the claim that incident of abnormalities has increased. Now here's where I'm really careful, because if you go back to the question, it says something about the number of chemicals in the environment has led to the increase of the incident of abnormalities. Okay. Now, what you have to be careful of, I don't have any evidence that the chemicals is what actually caused the abnormalities. Okay, so I'm really careful, at least when I state my conclusions, that I don't say that there's evidence to suggest that chemicals have caused an increase in abnormalities. Because I don't really know if it's the chemicals that's caused the abnormalities or something else. So I only feel comfortable saying that I can definitely say the incidence of abnormalities has increased. I don't like to go out on a limb and say what's caused it because I don't technically have the math here to prove that chemicals in the environment is what caused the abnormalities. That's not really the hardcore part of this class that we're going to go into. Obviously, there's not much of this class left. I think this is actually one of the last lectures. But that's something to note if you do actually do this in the future for somebody. Be really, really careful, especially if you're the one publishing the research, not to jump to conclusions that you really can't prove. Yes, we can prove that the incidence of abnormalities has increased, but we can't mathematically tie it, at least with the information we have, to it being chemicals in the environment that's actually causing it. So be careful with that. 7 says a company believes that it is a household name and estimates that 40% of U.S. adults know their brand. In a random sample of 300 U.S. adults, 45% say they know the brand. At a 5% level, is there enough evidence to reject the company's initial estimate? Okay, so, alright, what we notice here is their null hypothesis here is 40%, right? They believe that 40% know their brand. It's a percent, so I'm going to use a P. So P naught is equal, I'm going to write it as a decimal, to 0.4. Okay. Now, in a random sample, 300 U.S. adults, say 45 know the brand at a 5% significance level. Is there enough evidence to reject the company's initial claim? Now, we can see it says 45% here, which is obviously greater than 40%. But it doesn't necessarily say that they're looking to see that they're more known than what they initially thought, if that makes sense. So really and truly, it doesn't say, unless it specifically says, is there enough evidence to reject the company's initial claim and show that it's more than what they initially thought or less than what they initially thought. If it doesn't come out and say greater than or less than in some kind of form or fashion, what you're going to want to wind up using is P is not equal to 0.4. Okay. Alright. So this is another one where you can check your conditions. Obviously, if we're just looking at 40% of 300, that's going to be way greater than 10. If 60% of 300 is going to be way greater than 10. Your initial conditions here hold. It's always a good idea to do an eye check on those. We're using a percent here, so we're going to use one prop z-test. That should be an easy choice for you. If we come over here to try to find the value on the calculator, remember stat, we're going to go to test, number 5, which is 1 proportion z-test. The initial proportion, it was thought to be 40%. Okay, we have to find an x here. Now, we've done this once before. Let's try to make sure you know how we're doing it, right? In a random sample of 300 U.S. adults, 45% say they know the brand. So in order to find this x, so I'm just writing here, x equals 0.45 times that 300. That's how you're getting your x. Same way we were for confidence intervals. Okay, so if we do 0.45 times 300, you can do it directly here where the x is at. It'll give you 135. So if you really, really needed that step on the last one, I apologize. But here it is on this one. You're just multiplying to get that. So that's your x. Your x is 135. Your n is 300. So let's type your n in real quick. Okay. We decided to let it be not equal to because they didn't specifically come out and say greater than or less than. Okay. We calculate it, we wind up with a p-value equal to 0.077. Okay, so if I come over here, 0.077. Okay, now that's with not equals. Now this is why it's important to really state your conditions how you want it. For instance, if I come back over here, I go to one prop z-test. And let's say that they thought that it was greater than, because they wound up in their sample with something a little larger. then you'd wind up with a p-value that is much smaller, and then an alpha significance level 0.05, which is I believe what we're using here. Yep, at a 5% level. If you would have gone out, used your research, and changed your initial hypothesis or alternative hypothesis to greater than, you would have actually come up with a completely different decision using greater than you would using not equal to. Now, I know that's kind of hard for some people to gather, especially over just a GoPro YouTube video. But essentially, with the not equal to, what we wind up with here, I'll just rewrite it here, 0.077. Okay, so here, your P is greater than your alpha. If your P is greater than your alpha, you're going to fail to reject the null hypothesis. Okay, but like I said, if, let me just write it another color. So if we would have chosen to do our alternative hypothesis here, if it would have actually been P is greater than 0.4, we would have wound up with a p-value here that was equal to, I'll write p-value so you can differentiate that from p. So we would have wound up with a p-value that was equal to 0.039, in which case we would have rejected our null hypothesis and definitely believed that there's more of a presence of people who actually know who we are. Now I know that's confusing. Okay, if I choose not equal to, there's nothing to show that it's any different than what I said initially. But if I chose greater than, there is evidence to show that it is truly greater than, so it is really different. So it all actually depends on your initial null and alternative hypothesis that you choose. Okay, the same problem can give you two different results depending on your alternative hypothesis you choose to go with. Okay, so you have to be really careful, especially if you're doing it as a job, in which one you're going to choose. Here we chose not equal to because our boss was not really specific. If we could have gone in and said, hey boss, I think we're actually greater than, we could have showed it was greater than. But because we just said, I don't think that's right, I don't think it's equal to that, and we weren't more specific, we actually wound up showing that, hey, it doesn't appear to be any different than that. Okay, now that was kind of a whole lot of wish and wash in the talk, so hopefully you gained something from that insight. If not, don't worry about it. Just make sure you can do the math of this. I'm going to put it in a complete sentence on the board real quick, and we'll be one step closer towards the end of the lecture. Alright, so with an alpha equal 0.05 significance and a p-value of 0.077, we fail to reject the null hypothesis. There is not significant evidence to suggest the percent of U.S. adults who know the company is any different than 40%. Like I said, if we'd have gone through there and we'd have specified our alternative hypothesis a little different and said our alternative hypothesis was indeed P is greater than 0.4, then we would have actually come up with a different p-value. That p-value would have then been 0.03, what do we say, 0.039, and with that alpha value of 0.05, we could have indeed rejected our null hypothesis and said that there's more than 40% of people who know the company. But because the question was more vague, whoever set the question was vague and didn't specifically say greater than or less than or anything like that, then we had to use the not equal to, and we wound up with this conclusion instead. Okay, so it really, really matters how the question's asked. So please pay very close attention to that. Number 8, last example we have here, says a roof manufacturing company makes 26 gauge metal roof. They claim that the average thickness of their 26 gauge material is 0.02 inches. The quality control specialist regularly checks this claim. One production run, he took a random sample of 10 pieces of a metal roof and measured their thickness. He finds the average to be 0.0183 with a standard deviation of 0.00095 inches. At an alpha equal 0.05 significance level, would he reject this claim? Alright, so the null hypothesis here, okay, is that hopefully it is going to be that 0.02 inches, okay? So, null hypothesis is that it is equal, that is actually mu naught, which is mu sub 0, equal to 0.02. Okay, your alternative hypothesis, right? So, it doesn't once again say less than or greater than. He just has to check that it's close to this, okay? So, our alternative hypothesis is going to be mu is not equal to 0.02. Okay, because it doesn't specifically say greater than or less than. Just because our sample finds it to be greater than or less than doesn't mean we go with what our sample shows. Sometimes we just want to know, is it equal to or not equal to. We have to specifically say greater than or less than in the problem for it to, or indicate some kind of greater than or less than in the problem for us to actually choose that for our alternative hypothesis. Okay, so hopefully whoever tested this made sure that everything was independent and random, so we could check those conditions. So, like I said, we can't do anything on the back end for that if he done it wrong. But hopefully, we did all those right. Always a good idea to check your initial conditions, see if it makes sense, and if you're the one doing the testing, to make sure you do it right. Alright, so, which test are we going to use? Alright, if we're looking at it, we're only sampling 10 pieces. Okay, it does not tell us what the actual standard deviation is. We found a standard deviation when we ran our sample. Okay, so we're going to wind up using a t-test. Okay, p-value. So let's go over here and use the t-test. We'll go stat test t-test. Okay, we're going to use stats. Our initial mu naught over here was 0.02. 0.02. Our x bar from the problem, it is this 0.0183. 0.0183. Standard deviation he found in the sample was at 0.00095. So 3 zeros and a 95. Okay, he only tested 10 of them. Okay, and we want to see if it's not equal. If we come over here to calculate, we get a p-value that has a -4 at the end. So we need to move our decimal places 4 places to the left. So we wind up with 3 zeros and a 3, 1. So 0.1, 2, 3 zeros and a 3, 1. You really have to make sure you move that decimal, otherwise you will get this question wrong. So we need to make our conclusion. Our alpha value that we used here is what, 5%? Is that right? Yep, alpha equals 0.05. So alpha is 5%. P-value here was 0.00031, which means if I compare the two, that the alpha is clearly bigger than the P. If the alpha is bigger than the P, I'm going to reject the null hypothesis. Okay. Now all we got to do is write it in a formal sentence. And after we write this in a formal sentence, I will go over type 1 and type 2 errors, and we will be done for the semester. So let's take this to the board. Alright, so with an alpha equal 0.05 significance level and a p equal to 0.00031, I reject the null hypothesis. The data suggests that the thickness of the material is different than 0.02 inches. So this one's actually really interesting too, because what you can do is you can go back, obviously, you can change your alternative hypothesis instead of not equal to less than, and you can show that the material is actually significantly less than what it's supposed to be, right? Because obviously a customer's probably not going to care if the roofing material is too thick. They're probably going to care that the roofing material is too thin and subpar, okay? But that's not what it told us to do. It told us to check and see if it's different than. I'm sure once the guy checks and see, hey, it's off, it's different than 0.02 inches, it's not 26 gauge, he's going to go back and say, okay, my data showed it was really less than. I can go back and check that. If it's less than, we need to make some adjustments in our factory and get this material back right so that we can make sure that our company is providing a quality product for our customers. So I got one other thing I'm going to go over before we call it quits for the semester. It's type 1 and type 2 error. So hang on, we'll go over that in just a second. All right, so I got this nifty little chart here. If you don't like the way my chart looks, you can find a chart on Wikipedia. You can find charts on just a Google search type 1, type 2 error. You'll find all different types of charts laid out in all different types of ways with all different types of words that all essentially say the same thing. But here's my chart. Okay, your null hypothesis is true. Okay, let's start with it. So if you have a true null hypothesis and you don't reject it, you've done the right thing, right? You've made the correct inference. So this is what you want to do. If you have a null hypothesis is true, you don't want to reject something that's true. So if you correctly do that, you've done it right. But if you do have a null hypothesis that is true and you reject it, you've made an error. You've made what we call a type 1 error. And the probability of a type 1 error is alpha. Okay? So if I set my alpha significance level to be 5%, then the probability of a type 1 error is going to be 5%. Does that make sense? So the type 1 error's probability is alpha. Very, very important. Okay? A type 1 error happening means that you have a true null hypothesis, but for some reason you've rejected it. Now if we go to the other column, if your null hypothesis is false and you fail to reject it, so you've got something that's false, but instead of rejecting it, you fail to reject it, then you've committed a type 2 error. The probability of a type 2 error is beta. Beta is not something we go over in this very initial stat class. If you want to go over beta, you're going to take another stat class. But we know that beta is there. Beta is just the probability of a type 2 error. I won't make you find beta. It's not something you have to worry about. Okay? But you do have to know what a type 2 error is. Type 2 error is when my null hypothesis is false, but I fail to reject it. Okay? If it's false, what you really should do is reject it. If you reject it, you've done the correct thing. You've made the correct inference. So that's kind of how type 1 and type 2 error works. So let's try to do an example really quick of type 1 and type 2 error. Alright, so this example is right off of last year's test. It says we are testing a new shampoo to see if it makes hair grow faster. We know that the average rate of hair growth is 0.5 inches per month. We give our shampoo to the test subjects and measure their hair growth. The null hypothesis says the new shampoo increases hair growth. The alternative hypothesis says the new shampoo does not increase hair growth. A says, what would a type 1 error mean in the context of this problem? B says, what would a type 2 error mean in the context of this problem? And C says, which is worst, a type 1 or type 2 error in this problem? Please explain. So, what I will do is, I know that y'all don't have this. I'm not uploading my last semester's test to Blackboard because then everybody would have it. I might want to use it again in the future. But I will hold it right here for a minute or two. You can hit the pause button. You can write this question down if you'd like. And we will go through A, B, and C so you can kind of get a feel of how these type 1 and type 2 questions work. So, A on that problem says describe a type 1 error. Okay, so type 1 error in this problem would be that the new shampoo increases our hair growth. So our hair actually does grow out. Okay, I got a haircut, so I don't have much hair right now. But if I use this new shampoo, it would actually increase my hair growth. But after testing and running our hypothesis test and doing all the math, for some reason we determined that it doesn't actually increase hair growth, when it actually does. Does that make sense? So, type 1 error, if we go right here, type 1 error, null hypothesis is true, but for some reason we reject it. So here the null hypothesis was true. It does actually work. It increases your hair growth. But after we tested it, we determined that it doesn't. For some reason, the math, we determined it doesn't increase the hair growth. Okay, but it actually does. Type 2 error. Okay, type 2 error, if we look at our little chart here, that's when the null hypothesis is false, but we reject it. Or we don't reject it, sorry. Null hypothesis is false, and we fail to reject it. Okay, so here, null hypothesis is false. So the new shampoo does not increase our hair growth. It doesn't, not at all. But after testing, we falsely determined that it does increase our hair growth. So this shampoo doesn't work, but for some reason, after we run all the numbers, it looks like it does work. But it doesn't. So what we found is false. So which is worse? Is it worse to have a new shampoo that increases hair growth, but we don't think it does? Or to have a shampoo that doesn't increase hair growth, but for some reason we think it does? I think it would be worse to have a type 2 error in this case. Okay, it's not always worse to have a type 2 error, but in this case I think it's worse to have a type 2 error because, especially if I was the one trying to shell the shampoo, I would hate to shell a product that doesn't work and I sit there and claim it does work, because then customers are going to use it and it doesn't work, and then I'm going to have some really, really bad feedback. It would also stink pretty bad to have a shampoo that really does work really well, but think it doesn't, because then I'm going to throw out that formula and try to find a new formula. But in this case, I would rather throw out a formula that works than wind up with a formula that doesn't work and have very unhappy customers. So which is worse? You can write down whatever your opinion is here, as long as you have good justification for it here. But which is worse here? I'm going to say type 2. Because I don't want unhappy customers. With short hair. Type 1 and type 2 error. You can find a whole bunch more examples online if you want to go through a few more of them. I believe you might have one or two on your homework as well. The chart really, really helps people. So make sure you kind of familiarize yourself with the chart, and you should be good to go. It's been really, really fun. I'm going to try to do a review video before your next test. That's the hope. Hopefully I won't have any more tornadoes come by my house and lose all my internet and stuff and be late on anything. And I'll try to pump out at least one more video for a review for the semester. But I really appreciate y'all hanging on, doing the best you can with a given situation that we've had this semester. Any questions, let me know. And I guess I'll be talking to you soon, and we'll be figuring out how this last test and the final exam is going to work online.